All right. Now let's continue from last time. Last time we talked about the setup of linear systems with constant coefficient, which can be written as a vector y prime equals a times a vector, where a is a matrix containing all the coefficients. Okay. Then we say, well, because of the linear principle, what we have is our general solution is going to look like C1, a general constant, times a vector, plus C2 times another vector. Moreover, these two vectors are linearly independent. That's what we're looking for the general solution. For initial value problems, you just need to do additional steps. But for now, it's just this. Okay? Now, with that in mind, what are we having here? We did an example. We did an example and end up solving using a partially decoupled system. So it's nothing new. But once we solve everything in the old method, what we end up with is some solution looks like this. So clearly, we do have the format we want. Okay, which is C1 y1 plus C2 y2. So our principle was working. The only trouble is, now we want a more efficient way of solving these two vectors y1 and y2. Can we just see this matrix and get these two vectors right away without having to do the decoupled thing? Because in general, number one, decoupling is really complicated. It takes a long to write down. Seems not necessary because you already have the matrix. Why do you want to actually, reverse back to the individual ones? And second, what if you have something which is not partially decoupled? There is no way you can actually solve one after another, so you have to handle it as a whole in terms of matrix notation. So that's what we want to do next. So the question here is, how can I solve this? See this matrix and find these two solutions right away without having to do the decoupling thing. Okay, so the job is try to find y1 and y2. We just need y1, y2, remember? After that, C1, y1 plus C2, y2 is done. So just need to find two linearly independent solutions, okay, from this matrix directly. That's our goal. How do we do it? Well, the first thing we can do is we can simply just plot this, vector field of this system and try to see what we have. Well, looks nice. Good. And if you plot them really carefully and start to try to see some patterns, you will notice, okay, at somewhere, this line looks special. So if I put these two lines there, seems like the other solutions, if we even give you the, so I can even give you the straight line, streamline, here. Okay. We observe something very interesting. That is, if you start from somewhere else, you will follow the line and just keep going. If you follow the line and keep going. But if your initial value is on this orange line, or if it is on the green line, it will stay on this green line all the time without changing the directions. Okay? So these two lines are what we call a straight line solution. Remember, this is every possible solution, so you have infinitely many, but there are two, which are very special. Seems like easier to find than the other ones. Moreover, they are linearly independent. So finding y1 and y2 reduced to can you find the orange solution and can you find the green solution, because it seems like they are the easiest. Okay? So now our job is try to find this y1 and y2. These are called straight line solutions. You have a lot of solutions. Okay, if you just draw it. Okay. This is your x and y. Okay. Clearly, there are solutions looking like that. Okay, you can follow, whatever. Fine. Okay, but there will be two very special ones. That is this one here and this one here in general. Okay. These are called the straight line solutions. Okay, now our job is try to find these two straight lines. All right, once we find that, number one, they are totally linearly independent. Therefore, if we already have two solutions, they are totally linearly independent, we can just write everything else to be a linear combination of these two. So done. Can you somehow guess where these straight line solution come from what we already computed? we already know the solution looks like this way, right? We already know y1 is going to be and we already know y2 is going to be this. Can you see where the straight line come from? If you just take this out and take this out. Okay, what's going on here? What's going on here is I have something. Okay, I have a vector which is called -1/2, 1. Fine. This is the vector. Okay, particularly this one. Now what I have is I have a let's make it clear, -1/2, 1. So let's be careful here. Don't just write down something. This is -1/2, 1. Okay, that's the vector. Now what we have is we have e to the -4t times this one. What does it do? Think about it. It's basically a constant times this -1/2, right? So what is going to happen is you are going to multiply this vector by a constant to make it longer and shorter. So if you take t equals 10, maybe it's here. Okay. If you take t equals 5, maybe it's here. If you take t equals 0, maybe the other way around. Okay. If you vary t, the only part vary will be this one, which is a constant. The second part on here will not change. Therefore, what you're doing is you're just changing the size of the vector, keeping the direction the same. Therefore, all the point will move from here all the way to here. Okay? But it will stay on this line all the time. It will never somehow jump to here. No, it will actually keep on this line because this direction keeps the same. You're just changing the size of the vector. Okay? Similarly, for the second one, you have the same thing. You do have a vector 1, 0. Okay? And what you're doing is, by plugging in different t, you're just changing the size of this vector. So sometimes, when t equals 1, it's here. When t equals 10, it's here. But what you're doing is, let t vary, your solution will actually go all the way from here to here. Back and forth, and back and forth. Okay? Similarly, it will stay on here. So, it's not surprising to see that when we draw the vector field, we do have two vector lines, which are the two straight line solution. One was like that. Try to recall the graph. And one was like that. So these two are the straight line solutions you're looking for. Now if you try to check what we have here, I probably should use the reverse color just to stay consistent. Let's see. The green is here. The orange is here. Okay, exactly what we get from the vector field. So what do we have? What we have is a straight line, two straight line solutions. Each one look like a format like this, which is e to the lambda t times a vector. Okay, the first vector is -1/2, 1, which is in the direction of the green. The second one is a vector 1, 0, which is in the direction of orange. And we do have a e to the lambda t in the front. But what this one does is it will change the size of the vector, but it keeps the direction to be the same. Okay, so that's what we observe. So that's why we do have a straight line solution, because the solution can be written this way. Therefore, your t will only make your point move along this straight line, but it will never change the direction of the straight line. Okay, so this is settled. Number one, what do you mean by straight line solution? After we draw the direction field, that's where we have some graph like this. But what is the graph like this? A graph like this tells you this solution here, as you make t to be different from 0 to infinity, or even negative number, this one does not change the direction, only change where you are on this line. Okay. Similar thing for the other straight line. Therefore, it can be written in this way. That is, you have a vector which stay all the same all the time, but you only change the size of the vector to indicate you are here, 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 or here. Beautiful. Okay, so that's the first one. We have straight line solution. Okay, and seems like they have to look like this. A constant times a vector. Okay, this part tells you the direction of the straight line, which doesn't change with respect to t. So therefore, your solution will only move on this straight line. The second part is basically the time invariant part. Move along the line, which kind of makes sense also because you have y prime equals ay. If you just think about it, this is 2 dimension. But if you have 1 dimension, for example, y prime equals ky, of course you know the answer is going to be c e to the kt. Okay, so there's no surprising that in the 2 dimension, this one can still be something of this format, at least for the example we saw. Okay, so it's settled. Next time you see a matrix, look for something look like that. You should have 2 of them. Once you have 2 of them, you have 2 very interesting things. Number one, they must be already linearly independent because one vector is going this way, like we said in our example. One vector goes this way, the other vector goes this way. Then automatically they are linearly independent when you plug in 0. All right. Then, if you successfully found 2 of them, you can already write down y equals c1y1 plus c2y2. Where these two are just the 2 straight line solutions you just find. Because you need to. You want them to be linearly independent, and straight line solutions satisfy all of them. Okay. Moreover, that's very interesting because if you think about it, okay, for this system we just find, we actually find, okay, we do have one that is e to the negative 4t times this. That will give us this straight line. Moreover, because it's negative 4t, for big T, as t become bigger, these two actually goes to the middle. Okay. Keep in mind there was a c1 here, so not only we have this direction, we also have this other direction, okay, for any general constant. But let's just say, not only this one gives you this, it also gives you here. And the second one is give you this. Notice, this is a 2. That means as t become bigger, this one actually moves away. That's what we learned from 1 dimension, right? And along the line, it's just 1 dimension. So from here, you can start to see the trend. Then everything else will be a linear combination of the red and the green. That will give you something like this. Number 1, go down. Number 2, go to the right. Okay. Go down along this line. Meanwhile, go to the left by this line. Go up, go left, go up, go around. Why? Because every single vector, every single solution is nothing but a linear combination of these two. And these two, you already know where the trend is. Then even if I draw something within these 4 quadrants, separated by the green and red line, you can start to see the trend of every single solution. Okay? If that makes sense, there is even more reason for you to just find these 2 straight lines, because once you find these 2, you will know on one direction in the green direction, is it a attractor, a sink, or a source? And on the other direction, is it a sink or source? which is very easy to do because you can just look at this number here. If it's negative e to the negative t, when t become big, this one goes to 0, right? So it's going to be a sink. If it's bigger than 0, that means as t become bigger, you're going away from 0. Therefore, it's going to be a source. But once you know these two, you will know the combination of all the others. Okay? So that's even more interesting to find the straight line solution. Of course, the most important thing, how do you find the straight line solution? We already know, okay, we need these two straight line solutions. Second, it gives us a lot of information about the system. Now, how do you find the straight line solution? Assuming you already know the form. That is e to the lambda t times some vector. I just need to find this lambda. I just need to find what this vector is, right? And moreover, I should have two of them. They should be linearly independent. Okay, so what do we have? We just plug this one into this. All right, what is y prime? If the solution looks like this, y prime is nothing but e to the lambda t, take the derivative lambda, fine, a and b. Why? Because a and b does not depend on t. That's the whole point of the straight line solution. Plug in different t, your direction stay the same. Okay? What is that? That, if you group all these, that is just lambda y. If your y already look like that way. Okay, so this looks very like the one-dimensional case. Meanwhile, what does your y prime equals? It equals ay, so I will satisfy as ODE. Therefore, what are you looking for? You are looking for, okay, hold on, a, e lambda t, ab. You are looking for lambda and a vector ab satisfying y prime equals ay, which means satisfying lambda e lambda t ab equals a e lambda t ab, according to what we computed here and here. Okay, that means what? That means if you divide by e to the lambda t on both sides, because they are not 0, you are just looking for lambda times a vector, let's call it v, equals a times the same vector. Now you need to ask yourself, does it look familiar? A matrix times a vector equals to a number times the vector. We had this definition. This implies lambda should be the eigenvalue of A. And your V is going to be the eigenvectors of A. So it's settled. If you know how to find the eigenvalue and eigenvector of a given matrix, then automatically you can get lambda and the vector, then automatically you get all the straight line solutions. Okay? That's going to be awesome. A, find the eigenvalue, lambda, and find the eigenvector. Okay, V. Then you will be able to combine them to give you the solution e to the lambda t, V. That will give you the straight line solution. Okay, some other interesting properties. Number 1, how many eigenvalues do you have? Usually, for 2 dimension, a 2 by 2, you should have 2 eigenvalues. So you do have 2 solutions. Okay. Second, are they linearly independent? This we need to actually quote another theorem we had in linear algebra. I don't want to spend time to prove it, but I try to recall it. That is, the eigenvectors of distinct eigenvalues are linearly independent. The proof is very easy. Okay, so you can go back and check it online, or just go to linear algebra notes and try to see why this is true. So we do want two straight line solutions. And this one tells you, well, if you just go and find the eigenvalue and eigenvectors, you can have, number one, two eigenvalues, then two eigenvectors. Okay, and number two, the eigenvectors happen to be linearly independent all the time, as long as the two eigenvalues are different. Okay, so this is fantastic. You want two, and we do give you two in the general case. So that is settled. Finding the straight line solution is the same as finding the eigenvalue and eigenvectors. Okay, something to note. We will have some cases. Sometimes we have two eigenvalues, but they are the same. So we have one eigenvalue case. We call it repeated eigenvalue. For example, you have a matrix 2, 2, 0, 2. This gives you lambda equals 2, but only one lambda repeated for twice. You will not have two distinct eigenvectors. Therefore, you do not have two straight line solutions, but only one. You need one more. We will show how to do that later. That is for repeated eigenvalues. Second, you probably haven't have a lot of experience before with this, but sometimes you can have complex eigenvalues. Something like this. You can solve it. You can have lambda equals plus or minus I. Okay, that's when you have trouble. That is, how do I interpret E lambda T A B? Because now I'm going to have E I T A B. Okay, that's when you have another case. So that will be later. For later, that we will handle all these kind of cases. But for straight line solution, we need to add some restrictions. We need to have two distinct real. For the other cases, we need to handle it later. And for the other cases, you will not have two straight line solution. So this only works for two distinct real lambda. Therefore, you have two linearly independent eigenvectors. And therefore, you have two straight line solutions. And it's done. Okay? All right. How do we do it? Well, let's talk a little bit about eigenvalue and eigenvectors. It's a review, so what I will do is I will write down the definition and some properties. You can go ahead and look for them online or check your lecture notes from linear algebra. The first thing is definition. Ax equals the lambda x. Then lambda is called eigenvalue. Okay, x is going to be called the eigenvector corresponding to lambda. So they do appear in pairs. Do not match the eigenvalues with some eigenvectors from another eigenvalue. Okay, they need to come in pairs. Second, how do you do that? What you do is you basically are trying to say lambda x minus ax minus lambda x equals 0, which is a minus lambda I equals 0. And we know this one has a trivial solution, x equal to 0. But now, because you want an eigenvector, you want something other than this. Therefore, this one should have non-trivial. Okay, just 0 is not enough, because you don't have a straight line solution. 0, 0 times anything is going to stay at the point. So you want non-trivial solution. X, therefore you need to require this one equals 0. Otherwise you only have a trivial solution. So this will give you a polynomial of lambda, which is called a characteristic equation. Characteristic equation. And your job is solve the characteristic equation to get lambda. And once you have that, solve for x. to find eigenvector. Okay, this is something you know from linear algebra, so I will just give you some example to remind you a little bit. For example, find the eigenvalue and the corresponding eigenvectors of a matrix A equals 2, 3, 0, negative 4. So how do you do it? You take determinant of A minus lambda I, A minus lambda I, which is lambda lambda 0, 0. You want this one to be 0. Okay. Note, when we say I, it basically means I equals 1, 0, 0, 1. Then what we have is 2 minus lambda, 3, 0, negative 4 minus lambda, determinant equals 0, and for determinant we just had. This implies lambda equals 2 or lambda equals negative 4. Okay, we are going to call this one lambda 1. We are going to call this one lambda 2 to differentiate between the two eigenvalues. Therefore, each one is going to have a corresponding eigenvector. So lambda 1 equals 2, which means A x equals lambda x. We want to find x. Let's assign it to be A, B. Then 2, 3, 0, negative 4, A, B equals lambda, which you already know, 2A, B, which is 2A, 2B. Then 2 plus 2A plus 3B equals 2A. Negative 4B equals 2B. This implies B equals 0. Then the first one degenerates to 2A equals 2A. So A is free. A can be anything. So the vector looks like, which is A times 1, 0. So this is going to be your vector 1. Eigenvector for eigenvalues lambda 1 equals 2. What about A? Well, it's not hard to prove. If x is eigenvalue, A is an eigenvector of lambda, so is a constant times x. Okay, it's very easy to do. If ax equals lambda x, now of course cax equals c lambda x, and you move the constant around, you have a cx equals lambda cx, which means cx is also an eigenvector for the same lambda. Okay, from here you can see that, try to recall the concepts we had in linear algebra about eigenspace. I don't want to talk too much about it, so just check your notes from eigenspace to realize every time you have an eigenvector, you don't have a single eigenvector. You have a whole dimension of eigenvectors. Okay, if you have two eigenvectors, all the possible linear combinations of these two eigenvectors will be this eigenvector. So you do have some concept called eigenspace. And we just need one. The general constant, we can keep it for later. Okay? Now repeat the same thing for lambda 2, negative 4. So ax equals lambda x, 2, 3, 0, negative 4, ab equals negative 4a, negative 4b. What you have is negative 4b equals negative 4b, redundant. 2a plus 3b equals negative 4a. This implies b is free. Which means you just keep b as b, right? And the first one gives you 6a equals negative 3b. Therefore, a equals negative 1/2 b. So the eigenvector looks like this. which is b times negative 1/2, 1. Because any possible linear combination you can do, you can take this one to be your eigenvector, or you can take any multiple of this one, so you can change it to this one, which looks also a little bit nicer. And it doesn't really matter which one you pick, because basically your real eigenspace is going to be this one times any constant. Okay, but let's just keep this. So lambda 1 equals to v1 equals 1, 0. Lambda 2 equals negative 4, and v2 equals negative 1, 2. Or let's just use negative 1/2, 1, which really doesn't matter which one you use. That will be the complete set of linear of the eigenvalue and eigenvectors of the original matrix A equals from the definition. That's it. Very standard if you know how to do this. And usually if you have a computer at your side, one of the most important functions in MATLAB or Python or any scientific computing tool is if you give them a big matrix, they can give you the eigenvector and eigenvalues in really fast time. All right, now let's think about it. Why do we want this again? Technically, we want to solve this. So let's go back to the linear system of ODE. The reason you're doing this is you're trying to solve this. Okay, and you already find eigenvalue and eigenvectors. Then you have the straight line solution. What are they? E lambda t a b. So the first one is going to be lambda equals 2, okay, with the eigenvector 1, 0. The second one is going to be lambda to the negative 4. Lambda equals negative 4, the eigenvector. So what about the general solution? The general solution is going to be C1e period. We didn't do anything about decoupling. We didn't actually solve any differential equations. We end up solving an eigenvalue and eigenvector problem, and nothing worked. Moreover, are these two linearly independent? You just need to plug in 0. So basically, you're just looking at this and this and say, well, are they linearly independent? So very, very convenient. You can see this right away if you write down everything into this format. And that is beautiful. Okay, so let me write down the general process, and then we will give you another example. This is number 2, eigenvalue and eigenvectors. So number 3, how do we connect eigenvalue and eigenvectors? We have already done it. Now let's put it into a theorem. Okay. Okay. If A has an eigenvalue lambda and the corresponding eigenvector, that's called V, then the straight line solution E lambda t times V. Okay, note this is a constant, not a constant, this is a scalar times a vector. Okay, is the solution of y prime equals ay. So to find the straight line solutions, just find eigenvector and eigenvalues. That's step 1. Okay. Moreover, this eigenvalue lambda needs to be real. If it's complex, no straight line, which we will show later. Okay. Now that's already good. Moreover, if, remember, this only gives you a straight line solution. In order to write down the general solution, you need to make sure that you have two linearly independent straight line solutions. So if lambda 1 and lambda 2 are distinct, real, pay attention, it has to be distinct. It has to be real. If it's complex, fail. If it's you have two eigenvectors, but they are the same, fail. Okay. Real eigenvalues with eigenvectors v1 and v2. Then the general solution is the first straight line solution plus the second straight line solution, and all with any two possible free constant. Okay, so straight line solution is great. Moreover, if you have enough, which means you have two distinct straight line solutions, distinct we mean linearly independent, okay, then you already know the general solution because you already have two. All right, let's try another example. This time we already have the theorem. We don't have to keep thinking what we're doing. We can just go ahead and do it. Solve this. Y prime equals AY, which is given by 2, 2, 1, 3. Okay. What we can do is we can forget about every argument. We just go ahead and solve for eigenvalues. Okay. We can skip everything and just go to the determinant, which is 2 minus lambda, 3 minus lambda, 2 and 1 equals 0, which give you 2 minus lambda, 3 minus lambda equals minus 2 equals 0. The good news is you always have a polynomial, so 6 plus lambda squared minus 5 lambda minus 2 equals 0. You have two distinct real eigenvectors. Eigenvalues. So automatically you know this is going to work. We are definitely going to have two straight line solution, and lambda 1 equals 5. A general vector v1 is going to equals 5 times v1. Okay, and lambda equals 2, 2, 1, 3. So 2a plus 2b equals 5a. A plus 3b equals 5b. Putting together, you can have the first one, which is 3a equals 2b. Okay, or more precisely, b equals 3/2 a. Okay, you solve the second one, you will get the same thing. 2b equals a. Hold on, am I right? 5, 2, 2, 1, 3. Yes. 1 and 4. That's why. Okay. Now we'll change the whole thing. Okay, let me double check, make sure I did the right thing. Lambda squared minus 5. Yeah, that should be okay now. All right, 4a, 4b. Because the two equations should give you the same relationship. Okay. You have 2a equals 2b, or a equals b. All implies your vector should equals ab but then b equals a, so a, which is a, 1, 1. So the first nice v1 is going to be this. v2, oh, 2, 2, 1, 3, ab equals 1 times ab, 2a plus 2b equals a plus 3b equals b. This implies a equals 2b. Yes. Then you have the vector 2 is going to be negative 2b for my a and the b for my b. So of course, if you have, again, this is kind of boring, but if you have a computer, it can tell you really quickly. Either way, lambda 1 equals 4 with v1 equals 1, 1. Lambda 2 equals 1. v2 equals negative 2, 1. Then your y. I will skip the y1, y2 for the straight line solution, but you will know what I mean. E4t 1, 1 plus c2 e1t, which is just e to the t. Negative 2, 1. Technically, this is the first straight line solution. This is the second straight line solution. You can even draw them. One straight line solution go this way. Negative 2, 1. The other straight line solution goes this way. Moreover, because on 1, 1 it's a positive 4. As t become bigger, you leave 0, 0. So, okay. As t become bigger, you also leave because you have e to the t, positive 1. So no matter which way, you are going to be leaving the origin. Then what about something in between? You are still going to be leaving the origin. Okay, so that will give you something like this. Even though we didn't draw it. Okay, but you can imagine what's going to happen. All right, so this is clearly a source. Later we will show you how to determine if something is a source or a sink, and probably you already know. If your lambda is less than 0, your straight line solution is going to have something like this. If your lambda is bigger than 0, your straight line solution is going to have something like this. Of course, later we will think about what if lambda is 0, right? Or if it's complex. But for now, you can see, and then if you just combine them, do you have a sink? Your sink requires both are negative. So this is a sink. Okay. What about a source? Source, you probably want both to leave. Then anything in between will also leave, right? This one, anything in between will also come back because it's a linear combination. And finally, that's something we have, leaving and coming. Then you have something which is a node, like that. So sink, source, and node, or saddle, actually. Yeah, we already have the point, saddle. That's for later. But for now, you can actually already see like what's going on with this. Cool. So did I prepare an example? I prepared a different example, but I think the ideas are the same. Okay. The third example is something we can have, which comes from a harmonic oscillator. You have the, let me change it. This should be a y prime. You will have this code, so play with it. I'm just going over it really quickly. You have the frictions from with a 7 divided by m, and you have the spring constant, which is 10 k over m is 10. So somehow you have something like this. You solve it with eigenvalue and eigenvectors using MATLAB or Python. Then we calculate lambda 1 equals -5, lambda 2 equals -2, v1 and v2, which is different from what you see from here. But keep in mind, okay, the first one is definitely going to be a constant and multiply 1, -2. You can check by yourself. The second one is going to be a constant multiply 1, -5. Then this is taking relatively long. Then you can see in the direction of 1, -5, we will have the orange straight line. In the direction of 1, -2, we will have the 1, -2. Take it back. The 1, -5 is going to be the green one. 1, -2 is going to be the orange one. So we have two straight line solution. Okay. Moreover, you can tell in this direction, lambda is less than 5, which give you e to the -5t. For big T, this is very close to 0 because lambda is negative. Some similar thing for this. Then in both directions, it's going towards the origin. What about a linear combination of both? It will still go towards the origin. Okay, from here you can see, well, that's basically what we'll expect to be a sink. Okay, so that's what we have for solving the linear systems, but this time we do not use a partially decoupled thing. Instead, what we do is we go into the straight line solution and we find that, well, finding that is the same as finding the eigenvalue and eigenvectors. And then nice properties just emerge from this. Several things to keep in mind. The first one is two straight line solution. Requires two distinct real lambda. Then automatically we have some left over. What if we have a repeated real? Which means we only have one lambda, which only gives us one straight line solution, but we need two in order to get the general solutions. And also, what if you have complex lambda? On something you can actually think about it here, that is also like you have e to the lambda t, which give you a straight line solution, right? So probably I shouldn't do things in this way. I just need to say, well, you have something like this for you to think about. The third one is actually lambda equal to 0, which give you e to the 0t, which give you which only give you a point. So instead of giving you something with a straight line, it actually give you a point. Okay, so how do you actually draw the vector field for that is going to be very interesting. Okay. Second thing, which I want to briefly mention, you know, once you have the straight line solution, everything you need to do is just write down the general solution. But what about initial value problem? Well, to solve it, it's really easy. Let's assume you already have this ay, and y0 is x0, y0. Okay, and you already did know a or y is c1 e to the lambda 1t v1 plus c2 e to the lambda 2t v2. If you already know that the solution can be written as this, now you just need to plug in 0, which give you c1 v1 plus c2 v2. This one should equals your initial value x0, y0. So I'm just going to call this y0. Okay, which give you v1 plus v1, v2 c1, c2 equals y0. So what you're trying to do is, let's assume you have something like this. And your y0 is somewhere here. Okay. This is the first straight line solution. And this is the second straight line solution. So what you're trying to do is you're doing nothing but to rewrite this y0 as a possible linear combination of everything on this eigenvector direction. So what you're trying to do is you're trying to rewrite y0 under a new basis v1, v2, and write it as a linear combination of v1 and v2. That in linear algebra corresponds to a change of coordinate. So basically you have a linear system, right? And you have a matrix describing the dynamics. So what you have is you have a equals such. Okay. If you use a standard base 1, 0 and 0, 1, your initial value is in this, your solution is also in this. But now, as we know in linear algebra, you can also change this to be a different basis as long as they are linearly independent. And for two distinct real values, you can do that. Then for the same linear transformation, it will reduce. Okay. This one will reduce to something very, very simple. That is going to be lambda 1 and lambda 2, which is called diagonalizing A. Okay. If you try to recall, this is something, if you use Lay's book, is in chapter 5, when after you learn the eigenvalue and eigenvectors, is you can diagonalize A to be a P times P inverse, where P is given by exactly your eigenvalue vectors, and your D is going to be a list of your eigenvectors, eigenvalues on the diagonal. In another way, if you do a change of coordinate, the matrix becomes super easy. Do you know how to solve this? If you have something like y prime equals this, y. That's the best case, right? It's the decoupled case, completely decoupled case. You have x prime equals lambda y1x, y prime equals lambda 2y. Then you have x equals e to the lambda 1 t, y equals e to the lambda 2 t. So your general solution is going to be c1 e to the lambda 1 t. I should have a c1 here to be careful. C2 is here. C2 e to the lambda 2t, which give you exactly the same thing as before. Okay, you don't have to compute things in this way. Just want to show you the deep connections. Okay, this will be the solution you have if you do a change of basis. Okay, from here you can see if you can change the original basis to this, a new basis, then your original system will reduce to a diagonal system. And once you have a diagonal system, it becomes super easy. So basically the general solution, what you're looking at here is nothing but this, and then replace this to be V1, and this to be V2 for the general case. So you can connect actually, doing the eigenvalue decomposition of your final solution and connect it with the diagonalizing of the matrix A, because what you're doing was just a change of basis. So if you change your system, it's almost like you have a y, and you go to solve for y. It's the same as do a change of coordinate. Hold on. Let me think about how to write this. It's almost like solving this one can be reduced to solving this one, which is super easy because it's completely reducible if you do a change of coordinate. Okay, to get okay, and the change of coordinate of course go from the basis 1, 0, 0, 1, 2, v1, v2. So that's another way to put it conceptually. Okay, once you change the coordinate, the thing becomes super easy to do. And once you solve it, you just change everything back. All right. That's all we have for the easiest case. Two distinct real eigenvalues, which give you two distinct or linearly independent straight line solution. And then you have the general solution.